Hello everyone and welcome to the next lecture in the NPTEL course Machine Learning for Core Engineering Disciplines. In the last class we discussed about the concept of the learning rate and how it plays a very important role in the gradient descent method, and previously we have also understood the logic of the gradient descent method using the Taylor series, and we have also looked at the Hessian matrix which decides whether you have reached a local minimum or not. In the last lecture we also introduced the distinction between batch gradient descent and stochastic gradient descent, and in the latter method of stochastic descent what you do is you work with small batches, mini batches, or even a single data point, and that saves a lot of time. Training happens fast because the loss function computation is much faster if you work with a smaller mini batch of points. Now in today's class we will see some strategies to improve the convergence and make convergence smoother for stochastic gradient descent, and these have been developed over the years. So let us go ahead and look at this. So the topic for today is variants of stochastic gradient descent and as someone who is going to develop ML models, right, whether in core engineering disciplines or otherwise, you need to know, right, how the training process happens and what are the nuances and subtleties involved. So as you recall, the basic, right, equation of gradient descent is as follows. You update the parameter vector, right, k plus 1, so beta j k plus 1, where k is the index for the iterations, and here I am writing this for the jth, right, feature, sorry, jth parameter in the ML model, and we are looking at it after it has been updated in the kth iteration. So beta j k plus 1 is equal to beta j k minus gamma, the learning rate, times the gradient of the loss function at iteration k with respect to the parameter beta j. So you know that k is the iteration number, and gamma is the learning rate. Okay, and this gradient, right, this gradient is from a single sample or data point or from a mini batch. Right, a few points that have been selected to prevent you from spending too much time on computing the loss function or the gradient. Alright, so this is the basic form of the stochastic gradient descent, where the gradient comes from a single sample or from a mini batch. The problem with this is that it is very noisy, right. This improves the speed greatly, because you have to work only with the loss function from one data point, but makes the training noisy. So to deal with this problem, several strategies have been developed over the years, and we are going to discuss a few of them here. So what are these strategies? The first one is called stochastic gradient descent, SGD, with momentum. Okay, And by the way, the original stochastic gradient descent, right, the basic stochastic gradient descent was developed in the 1950s. And this SGD with momentum, this is fast forward to the 1980s. So what is this momentum? So basically in SGD with momentum we introduce a so called velocity vector which accumulates past gradients and thus dampens oscillations in regions of varying gradients or accelerates them, accelerates parameter updates when the gradients are steady. Right. So, you are accumulating past gradients. So, if these gradients are highly oscillatory, then you will dampen out the updates of the parameters, whereas if the gradients are fairly smooth, then you accelerate the parameter updates. Okay. And this is implemented as follows, right. So, you have a velocity vector associated with every parameter. So, I am writing Vj. So, j is the index for the parameter and k is the index for the iteration, that is equal to eta times Vj k minus 1 plus the gradient of the loss function versus beta j at iteration k. This eta is called the momentum coefficient and it lies between 0 and 1. Right. So, this factor, right, it controls how much of the previous gradients are included, right, in training. Okay. Obviously, if this eta value is low, then that means you are discarding the previous momentum, right, you are weighting the previous momentum less and you are majorly considering the current value of the gradient of the loss function. However, if this momentum coefficient is higher, then you are giving more weightage to the previous gradients because this factor is higher and you are simultaneously including the current gradient as well. Okay. So, this is how the velocity vector is defined, and then you update the parameters as follows. Your beta j k plus 1 is beta j k minus gamma the learning rate times Vj k, right. So, this is the learning rate and this is the velocity, right. So, you can now see that this accumulation, right, through the velocity vector can either accelerate or decelerate the training process, right. So, thus the inclusion of the momentum of training via the velocity vector can speed up training. Okay. So, this was SGD with momentum. The next type of stochastic gradient, right, which came about was much later, right, in about the 2010s, and that is called Adagrad, right, or adaptive gradient. So, all of these later ones, these are from the 2010s, right. This one and the subsequent ones are from 2010s, right. So, here what we do is, instead of having a momentum vector, what we do is we adapt the learning rate individually for each parameter based on the cumulative sum of past squared gradients, right. Instead of directly taking the gradient, right, as was done here, we look at the cumulative sum of these past squared gradients, okay, and then we adapt the learning rate. So, this happens as follows. You write the update of the Adagrad optimizer as follows. So, your beta j parameter at the k plus 1th iteration is equal to beta j k minus gamma, the learning rate, divided by g j k, which stores the squared gradients, plus epsilon, right, a small term to prevent division by 0, times the gradient of the loss function versus the parameter beta j at the kth iteration. And like I said, this g j k is storing, right, the squared gradients as follows. Right, and I had mentioned that this epsilon is a small constant to prevent division by 0, right. So, essentially if g j k is large, so the gradients are large, the learning rate, the effective learning rate, which is this, is lowered. Okay, and that is what we want, right. If the gradient is already large, you do not really need a high value of the learning rate, right, automatically the parameters will change by a lot, right. However, on the contrary, if g j k is small, right, the effective learning rate will go up, right. Here the gradients are small, so you need to increase the gradient rate to increase the learning rate to accelerate the training process. Okay. So, this leads to these factors lead to smoother, right, because you are not taking very high steps if the gradients are already large, and faster training. If the gradients are low, you accelerate the training. So, that is really advantageous, right, that you can make the training smoother and you can make it faster, so that the training can be done with less amount of computing power, and that is really important these days. Okay. So, this was in 2011, and then in 2012 there was another variation of stochastic gradient descent that was proposed, and this is called root mean squared propagation. RMSprop. So, the next variant of SGD is RMSprop, short for root mean squared propagation. Okay. And this came about in the year 2012, and this uses an exponentially weighted average of the squared gradients to scale the learning rate for every parameter, right. So, we have to accumulate these exponentially weighted average. So, the RMSprop employs exponentially weighted average of square gradients to scale the learning rate. For each parameter. So, what this means is that you also start forgetting, right, the gradients beyond a certain point. It is not just that you accumulate the squared average, beyond a point what happened several iterations ago, that is not important, right. So, we need to exponentially weight them. So, we need to sort of forget the memory of large gradients from far ago. So, this is done as follows. So, you accumulate the exponentially weighted average Ejk as rho times Ejk minus 1 plus 1 minus rho times delta L at the kth iteration versus the jth parameter whole square, right. So, you can see the difference from the previous case when we had Adagrad, right. So, here this G simply accumulated the squared gradient, whereas what we are now doing is we do not fully accumulate it, right. There is a decay rate that is employed. So, there is a decay rate again between 0 and 1, and this decides how much of the previous squared gradients you are going to take and what is the current contribution going to be, right. So, this is the squared gradient contribution. The second term is the squared gradient contribution from the current iteration. Okay. And then obviously you will go ahead and update the parameters in a manner similar to what we had done, right, for Adagrad. In this case, instead of using the accumulated squared gradient, you will use the accumulated exponentially weighted average of squared gradient. So, you do not necessarily accumulate things from very far ago, right. So, the final equation is pretty much the same. It reads as beta j k plus 1, right. So, the jth parameter at the k plus 1th iteration is the jth parameter at the kth iteration minus the learning rate times the gradient versus the parameter of the loss function at the kth iteration scaled by the exponentially accumulated squared gradient, right. So, this is again a small positive number to prevent division by 0, okay. And this is the exponentially weighted average of past squared gradients. Okay. So, this is nice because due to the decay rate employed, the RMSprop solves the issue with Adagrad with regard to reducing the learning rate too aggressively. Due to past values of large squared gradients. So, essentially in Adagrad the problem was that the parameters could be, or the learning rate could be reduced by a lot if the gradient values in the past were very high. However, RMSprop says that you should also have a forgetting factor, right. You should have an exponentially weighted average, so that only the immediately near squared gradients do contribute to the manipulation of the learning rate of the model, right. So, I hope it makes sense to you as to how RMSprop is different from Adagrad. Okay. So, let us go ahead and study the last variant of stochastic gradient descent that we want to cover, and that is called ADAM, or adaptive moment estimation. Right, and this came about in the year 2014 or so, and what we do here is we start thinking in terms of the moments, right, of the gradient. So, the ADAM method includes the exponential moving average of both the gradients, which are the first moment, right, of the loss function gradient, and the squared gradients. Which are the second moment. And this effectively combines the features of momentum, right, wherein we were only looking directly at the gradient, not the gradient squared, and RMSprop, which includes the squared gradient but also has a forgetting factor and includes the exponential moving average, right. So, now we have to have two variables, one which will accumulate the velocities and one which will have the squared gradients. So, you do it as follows. So, you accumulate the velocities. So, Vjk is eta Vjk minus 1 plus 1 minus eta delta beta j times the gradient of the loss function at the iteration k, that is the accumulated first moments, and then you also accumulate the squared gradients, the second moment. So, that is rho times Ej at k minus 1th iteration plus 1 minus rho times the gradient of the loss function versus the parameter Bj at the kth iteration whole square, right. So, this is the second moment, right. So, that is how it is combining the features of both momentum and root mean squared propagation. So, this is the mean of gradients, right, with a forgetting factor, right, and this is the mean of squared gradients. Okay. So, I hope this makes sense, and there is also another important thing that has to happen when you are implementing ADAM, which is called bias correction. Essentially whatever these means you are calculating initially, right, you can't use them directly, right, and therefore you have to correct them. So, you define the bias corrected, right, velocity. So, that is Vjk divided by 1 minus eta to the power k, and similarly Ej hat k is Ejk divided by 1 minus rho to the power k. So, this is k in the exponent, right. So, you can see that initially, right, the value of rho is something between 0 and 1. So, this value, right, 1 minus rho, right, would be 1 minus rho would be close to 1, right. So, you will directly take this, sorry, 1 minus rho would be a small number. So, you take a larger value of Ejk and Vjk, but as your k value keeps on increasing, this eta to the power k tends to 0. So, your denominator will become close to 1 and then you stop increasing the values, right, of Vj and Ej, right. So, this is a really nice feature of the ADAM method. Alright. So, once this bias correction has been implemented, which is particularly important for the initial iterations, right. So, initially like I said, k is 0 and then is just 1, and then finally you will start getting lower and lower values and this will increase. Alright. So, the final update set of equation is beta j k plus 1 is equal to beta j k minus gamma times Vj hat k divided by square root of Ej hat k plus epsilon, okay. And eta and rho, obviously you know these are the decay rates for the first and second moments. Alright. So, this brings us to the end of the discussion on stochastic gradient descent, right. Before ending, I just want to tell you that there is also other types of algorithms which include the Hessian, right. There are other algorithms which include the Hessian, right, and these are obviously faster because you are also capturing the second order derivatives in the Taylor series, but they are more expensive, right. So, these are certainly more expensive, but can converge faster due to information on second order derivatives. One of the most famous algorithms in this category is the LBFGS algorithm. So, this is limited memory BFGS algorithm, and BFGS stands for the initials of the people behind this. So, that is called Broyden, Fletcher, Goldfarb, Shano algorithm. okay. And the main thought process behind this is what is limited memory BFGS. So, in contrast to the original BFGS, which uses an approximate Hessian, and remember the Hessian has size p by p, right. So, where p is the number of parameters. So, here the algorithm simply stores some vectors which approximate the second order derivative information. And because you do not need to store the entire Hessian, right, although BFGS already uses an approximate Hessian, you do have to store it, right. So, here you just have to store some vectors instead, right. So, that is why it is called limited memory BFGS, right, because you have reduced the memory requirements for the BFGS, which itself is going to be very large. If you have billions of parameters in your neural networks, it can be very expensive memory wise to store this, right. So, I hope you get the basic idea behind the BFGS method. The math behind this will require a lot more number of lectures. So, I am not going to go into it since this is an introductory course, but I suggest that for those who are interested you can look into it at several other sources. So, this brings me to the end of this lecture. We have discussed 4 different variants of the stochastic gradient descent method, including SGD with momentum. We discussed about RMSprop, Adagrad, as well as Adam, and the main idea here was that we have to adapt the learning rate, right. We cannot use the same learning rate throughout the training process, especially because SGD uses a mini batch or a few points. So, your gradient is going to be inherently stochastic, right, it is going to fluctuate. So, you have to, in the best case scenario, include an exponentially weighted average of both the first order information and the second order information, the squared of the gradient, and this right allows you to scale the learning rate. In regions where you need to, the gradient is low, you can accelerate, and in regions where the gradient is high, you can decelerate, right. So, that is the whole idea of these kind of approaches to stochastic gradient descent. And finally, I also explained very conceptually what the LBFGS method means, the limited memory Broyden-Fletcher Goldfarb-Shano algorithm, right. That is a second order algorithm, and mostly in machine learning we simply resort to first order algorithms because it is very expensive to go near the Hessians, right. So, I hope you enjoyed this lecture, and thank you for coming today. I look forward to seeing you next time.